Now we're going to consider a 3D problem on internal forces. As you can see in the picture, the hand crank is subjected to a vertical force of 50 pounds. Assuming that the crank is fixed to the shaft at B, determine the resultant internal loadings at point A. Now point A is this point right here, which we're going to assume is on the centroid of the cross section at that point. And you can see that we've been given a coordinate system x, y, z to start with. There's x, there's y, and there is z. Now, this question of what's going on at A, what are the internal forces there, is going to require us to develop a reasonable approach to doing the analysis. So let's go ahead and write what that approach is going to be. Our usual way of starting these problems is to draw some sort of free body diagram, and in this case, we can make a method of sections cut directly at A to start off, and we don't really have to solve for the reactions at B if we don't want to. So let me propose that we do a method of sections at A, and once we make that cut, I'm going to consider the coordinate system that we're going to use, because as you may have already noticed, the force, the 50-pound force, is not oriented in one of the directions of the coordinate system that's been given. So we have to figure out how to deal with that. Once we figure out how to deal with the coordinate system, we can go ahead and solve the problem, as you'll see. And then the third thing I want to do is introduce a vector analysis, which will give you a different perspective on the problem, and maybe it's a way of looking at the problem that will make a little more sense to you and resonate with you more than the scalar approach, which we're going to pursue in parts 1 and 2 of the solution. Okay, so what we're going to do is we're going to start by making this method of sections cut. At A. And I'm going to try and draw this in a 3D way to make this very clear what we're trying to do here. Okay, and then the handle comes out this way like this. The force is 50 pounds oriented down that way. Okay, now the coordinate system that we've been given is, there's the y direction, there's the z direction, and then the x direction kind of comes out that way. And if we were to sort of look through this object, the origin of that coordinate system would be back in there. Now, one thing that we are told is that this angle, the angle between the force and the z-axis, is 30 degrees. So the first thing we can do is we can project that 50-pound force onto the coordinate system that we have. So for example, if we wanted to project that onto the y-axis, what we would do is we would find out that Fy is 50 times the sine of 30 degrees. That's equal to 25 pounds. And F in the z direction is going to be minus 50 times cosine of 30. And that's equal to 43.3 pounds. Okay, so the 25-pound force is sort of oriented that way. The 43.3-pound force is oriented in the z direction that way. Okay, now I threw the minus sign in there on the FZ calculation because obviously it's going in the negative z direction. Now that we know the way these forces are acting in the coordinate system that we are given, the x, y, z coordinate system, we can go ahead and do a little work to try and figure out how these things are going to interact with each other and what the internal forces at A are going to be. In order to do that, I'm going to propose to you that we do a scalar analysis. And in doing this scalar analysis, I'm going to show you a technique where you can take a 3D problem like this and do a series of 2D projections to get at some of the information that you want. So when we start looking at the coordinate systems, we certainly have to consider Fy and Fz, which we've already done, but I'm also going to suggest that you look at different views of the structure to figure out what sorts of reactions are going on back at point A. Okay, so the point of what we're going to do now is to consider the reactions that we're going to find back there. Let me start a new page. and show you what I mean. So for example, if we take a side view of the structure, what we're going to find something that looks like this. Okay, so here's point A back here. Here is our y-axis out this way. There's the z-axis, and we've got the forces out here. The ones we can see are 25 pounds and 43.3 pounds. And this is the view if I were standing on the positive x-axis looking back at the structure. Now the reason this is a useful view is because I think it's a bit more clear here that I could look at this and I would say, well, there's a shear force V in the z direction here. There's going to be a normal direction force. There's going to be an N, let's say, in the y direction. And then there's also going to be an M here, a moment. And this moment is going to be around the x-axis. Okay? Now, if we do that, it's really clear that we're going to be able to write N in the y direction is minus 25 pounds. We're going to write V in the z direction is 43.3 pounds. And then M around x is going to be simply 43.3 times 7 equals 303.1 pound inches. Now that 7 inches is the moment arm, which is that dimension right there. Now, we actually have to look at this moment in the x direction. We're doing this in a scalar way, and so to work out the direction of this, we realize that it has to point the other way from where I've drawn the arrow. So I'm going to put a minus sign there and make sure that we emphasize that this is a counterclockwise moment. Let's go ahead and draw the top view of this. If I'm standing on the positive z-axis and looking down at the structure, here's what I'm going to see. I'm going to see the crank down here. We've got 25 pounds going that way. Now I don't see in this view the 43.3 pound force because it's going along the z-axis and I can't see it from this top view. This dimension here is 3 inches. And then back here at A, I'm going to be able to write NY. We've already solved for that. I'm also going to look at a V in the x direction. And I'm going to look at a moment, let's say M, and this is around the z-axis, MZ. We've already solved for NY, so I'm not going to solve for that again. You can see clearly that Vx is 0 because there's no external force applied in the x direction. And so what we find out from this is that MZ is 25 pounds times 3 inches is 75 pound inches, and it's in the direction that I've already drawn it. Okay, it's in the clockwise direction. Now we've got one more view we can look at, and that is the view from the negative y-axis back towards the structure. So let's look at the end view. And I'm going to try and draw this in sort of a 3D kind of way so it's a little bit more clear. Here we are standing on the negative y-axis, looking down the structure. There is our 25 pound force. There's our 43.3 pound force. Okay, so here's point A. There's the z-axis. There is the x-axis. And what you can see in this view, and the thing I'm going to emphasize in this view, is that if we project this y-axis back this way, you can see that that force, the 43.3 pound force, is actually going to induce a torque around that axis. Okay, and that torque, T around the y-axis, is going to be equal to 43.3 times 3 inches, which is this distance right here. And that's just 129.9 pound inches. Okay, now the way that rotation is going, it's actually negative. Okay, by the right-hand rule around the y-axis, we find out that the negative sign is there, and you can see that it's opposing the 43.3 pound force, which is tending to put a moment or excuse me, a torque in the opposite direction on that. Okay, so in summary, at A, we can find out that there is a normal direction force that's in the y direction, and that's 25 pounds, and in fact it's oriented in the negative y direction. We found that there was a shear force Vz, and that shear force was 43.3 pounds. It was positive in the positive z direction. We found out that the V in the x direction, the shear in the x direction, was 0 because there's no externally applied load in the x direction. We found a moment around the x-axis. That ended up being 303.1 pound-inches. We found a moment around the z-axis. That ended up being 75 pound-inches. And in fact, the clockwise rotation of that one made it a minus 75. And then we found Ty is minus 129.9 pound-inches. So what I hope you saw out of this is that drawing a series of sort of 2D projections was a way to enable us to see what was going on at point A, even though this is a 3D problem. And that's a really useful tool that you can use as you go through and try and solve especially 3D problems. What I'd like to do is show you a vector approach to this problem. And what we need to do first is find the moment due to the external force. Okay? And to do that, what we need to do is the moment due to the external force is going to be r crossed with f, where r and f are vectors. So the first thing we need to do is define our r and f vectors. So r, in this case, is going to be 3i plus 7j plus 0k, and the units there are inches. Okay, and that's just from the geometry of the crank, locating point A and the point where the force is applied. F, as we solved for before, is going to be 0 in the I direction, plus 25 in the j direction, minus 43.3 in the k direction. That has units of pounds. So when we do the cross product, we're going to get m is equal to 3i plus 7j plus 0k crossed with 0i plus 25j minus 43.3k. Okay, and if we start doing this, we find I crossed with j, that gives me 75k. Then we get I crossed with k gives me a minus j, and the minus j combined with that minus sign right there gives me a plus 3 times 43.3 in the j direction. We're going to subtract j crossed with k goes down to I. It's 743.3 in the I. So m, due to the external force, turns out to be minus 303.1 in the I, plus 129.9 in the j, plus 75 in the k direction. This has units of pound inches. Okay? So we use vectors there to find the external forces impact at A in terms of the moments and the torques. And all we have to do now is realize that the moment at A as a vector is equal to the opposite of the moment due to the externally applied load. It's an equilibrium argument. And all we have to do is look at those numbers. So just to remind you, we would get minus 303.1 in the I direction, plus 129.9 in the j direction. Sorry, that's a minus there. Plus 75 in the k direction, pound inches. And what you notice is that this thing here is what we called mx earlier in the analysis. That is called ty, and that is mz. So you can see that the vector approach is a little bit more powerful in the sense that we can solve for all of these things simultaneously by doing the cross product. It's a little bit less physical, I think, because by drawing the series of 2D projections, you can get a better feel intuitively and physically how the external forces create these different forces and moments at A. So a quick review is we did this 3D problem by doing a method of sections at A and considering the coordinate system, and in particular we did a series of 2D projections. And then we also showed the interpretation which used the vectors, which constructed the r cross f vector, the moment vector due to the external force, and equated that to the moment at A.